Okay, welcome back. So now we looked at the chord class example, and now we'll look at another class example, which is actually a class called array. And we'll see some other things that didn't really come up in the chord class example. And one thing that's going to come up in this example is we are going to have some dynamic memory allocation, meaning with the keyword new. So you might recall from 165 that we can do that in C++ with operator new to dynamically allocate a new data value, where the thing that we allocate could be either a single entity of that type, like dynamically allocate a single integer or allocate an array. And same idea also applies to class objects. And one of the things that's going to happen then in this array class is one of the member variables is going to be a pointer of type int that points to an array of dynamically allocated integers on the heap. And one thing that you have to think about is, what does that mean in terms of things like the copy constructor and the overloaded assignment operator? Because in the chord class, in the assignment operator and the copy constructor, right, we just copied, for example, x from one object to the current object, or y from one object to the current object. But now we have to think about this when dynamic memory allocation is involved, right? And how are we going to properly handle that? And so we'll look at a couple of versions of this array class, but we have to think about those kind of issues, right? Now that things like dynamic memory allocation are involved, right? So what kinds of things need to happen in the copy constructor and the overloaded assignment operator in order to be able to make a true proper copy of the object. And so to do that in the correct way, right, it's going to be a little bit more involved than just simply copying, the member variable from the other object into the current object. And we'll see why that's the case. But so one of the member variables is now going to be this array of dynamically allocated integers. But the thing is, we have to think about, well, what does it mean to make a true copy? Well, a true copy would mean that if we have multiple array objects, they're each going to maintain their own separate arrays on the heap, right? But for example, if we're doing a statement like ARR1 equals ARR2, right, to invoke the assignment operator, where ARR1 and ARR2 are both array objects, well, we still want them to each maintain their own array, right? It's just that the two arrays would have the same values, right? So if array 2 has an array of integers with the values 1, 2, 3, 4, and 5, then array 1's array that it points to would have those same values. So that's what we mean by a true copy, right? Because if you do it that way, then you could later change, for example, array 2's array without that affecting array 1 and vice versa. So that's really what we want to ultimately do. But we have to think about what it's going to take to achieve that, right? Because that's not what would happen by default, right? If you think about the default behavior of the copy constructor and the overloaded assignment operator. And we'll first look at the version that's not going to be right, and then we'll look at the correct way of handling it. So we'll switch screens here. So the first version is what we sometimes might call a shallow version, the shallow copy. And then we'll look at the deep copy version, which is going to correctly make the copy for us. So this is the array, the shallow version of the array class. So we have at the top here, the input and output operators, as we had those also in the chord class. We have a default constructor here that can take one argument or no arguments. We also have a copy constructor, which we saw that first in the chord class. So we know that with a copy constructor, you pass in the class object by reference, right? Because we know that we can't pass it in by value because that would be trying to endlessly, call the copy constructor. And beyond that, we've said that really in general, you should always be passing non-primitive types like class objects by reference. So here we passed it by constant reference, right? Since the object that we're passing in does not need to change inside the constructor. We have a destructor written out here. We have a function to return the size. And then we have some of the same operators that we had in the chord class. So things like the assignment operator, which is set up in a similar way. We have equal, equal, not equal. And then a couple of new ones are the bracket operator or the subscript operator. And so what we're going to see is that there's also going to be two different versions of operator bracket or the subscript operator for working with both non-constant and constant objects. And so the first one here is, and the name of the function is just operator bracket. And the return type here is int ampersand. And then we have an integer number that's passed in. And so the idea is that this is the array, a class that we're calling an array, but one of the member variables is the pointer to the actual array of integers. And so we still have to think about how you're going to ultimately access the actual array itself, right? Because the array itself is not, directly part of the array object. Because the array object in terms of member variables has two member variables. One is size, the number of elements in the array. The other is a pointer named PTR, which points to the beginning of the array, where this array is going to be dynamically allocated on the heap, right? Meaning with the keyword new. And then we use size t there, but you could also have used int, but that's just referring to the size. And then the other is the pointer variable of type int star. And so the array itself, the idea is the array itself, the actual array that's storing numbers, in this case integer numbers, is not part of the array object, but the array object is going to point to that array that's located on the heap, right? The heap area of memory. So we still are going to need things like the bracket operator, because that's how we're going to actually access a particular location in the array of integers that's on the heap. So the integer that we pass in here is an index number that we will use to access a particular location on the array that PTR is pointing at. So PTR itself points to the beginning of the array, but we can ultimately access any location in the array by using a combination of PTR and the proper offset. So that's the integer number that's passed in. But we also have another version of operator bracket here. And this one you'll notice is const. The function itself is const. So these are both member function for operator bracket, right? Because that one has to be implemented as a member. But the second one here, it does have the same prototype in terms of parameter list. So one thing we can think about is, well, how are we distinguishing, this version of operator bracket from this version of operator bracket? We're not, in this case, we're not using a dummy parameter like we did with the increment and decrement, but what we are doing is one of them is constant, the other is not constant. Because depending upon where you refer to operator bracket, you may or may not be changing an element in the actual array of integers, right? If we do something like, and again, maybe the name of the array object is ARR1, and then we do a statement like cout ARR1 bracket 0. What we have to keep in mind is that since the array object itself does not have an array directly within it, but all it has is a pointer. So when we say ARR1 bracket 0, that is a function call to operator bracket function, where the number 0 would be passed in. And what's going to have to ultimately happen is that number that's passed in, along with the pointer PTR, those two things together are going to have to be used to access the right element in the array of integers. In that case, right, we don't need to change it. So it's okay if we return a value that's not going to be usable to change the array. So this version is constant. So, and we know that means that inside the function, of course, we can't change anything with regard to the number of variables, meaning that we can't change the array that PTR is pointing at. And also the return type for this version is by value, integer by value. Because again, we don't want whatever we're returning back, right? We don't want that return value to be usable to change the actual array itself. So that's why we're returning by value, or you could potentially return by constant reference also, but in this case, we're just returning by value. And then with the first version of operator bracket, we are returning a reference. And because with this version, the non-constant version of operator bracket, the whole idea is that we can use that return value to change the actual array of integers. So the first version of operator bracket could be used like with a statement like this. Now, again, this is a very important realization. We have to always distinguish between the array object, which just simply means an object with the class name, which the name of the class itself is array, versus the actual built-in array of integer numbers, right? Those are two very different things. ARR1 itself is not an array, but it is a class object which has a pointer member variable that does point to an array of integers. So the function call here is calling operator bracket, right? So a statement like what we had here has two different function calls, right? We got to call operator bracket, and then we also have to call the assignment operator to ultimately store 5. And so what's going to happen is we do this function call, meaning this type of function call shown here, ARR1 dot operator bracket, and then 0, assuming we want the number to be stored in index 0 of the array of integers. And so what that's going to do, and we'll look at the body of that in a moment, but what that's going to do is we're ultimately going to have to use PTR to actually refer to a location in the array. PTR along with the number that's passed in. So that's how we actually will refer to the array. So that's the type of logic that's going to be happening inside of operator bracket. And the array is dynamic, so we will also see the keyword new and delete come up in this example as well. So everything is done on a dynamic basis. So that's the idea with operator bracket. You know, a statement like this, you could do that by calling the non-constant version of operator bracket, because this one is allowed to change. In this case, we have to work off of PTR, the pointer, right? But we're able to change that array through PTR. And then what it does, because the return type here, you'll notice is int ampersand, right? As opposed to something like array ampersand. Because what we have to do ultimately, when you think about an assignment statement like this, is we have to return a reference to a location in the array of integers, because that's the only way, right, that we can ultimately have the value 5 be stored there. And this actually goes back to something that we really first talked about in that came up in chapter 9, when we talked about the idea of a dangerous reference return or a dangerous pointer return. You might recall that we said that that was referring to the situation where your return type was a reference of one of the member variable types. So like, for example, in the time class, we have hour, minute, and second as integers. But if we have a member function that has a return type, you know, int ampersand or int star, then that would be what we consider a dangerous reference or dangerous address return, right? Because as we saw, you could use that function call to, you know, that reference return value or pointer return value could be used to change the object without going through the set function. We're doing that here, right, in fact, because that's exactly what happens, right, if you have int ampersand as the return type. But we're doing that on purpose, right, because we want to be able to use operator bracket with our array objects in the same way that you would use the brackets with a primitive array, right? So within a primitive array, it's the name of the array, right? And then the index numbers in the brackets. And then on the right-hand side of the equal sign, the value that you want to store there. The whole idea is that just like with everything else with operator overloading, we want to be able to do that, but with an array object. So that's why we want to have the return type there in terms of integer, in this case, reference to integer, because it needs to be a reference if we want to be able to actually change the array itself, right, that PTR points at. So it needs to be a reference rather than a copy for that to ultimately be possible. So with the first operator bracket, the return type is in ampersand, and it's not constant. With the second version of operator bracket, it is constant, right? So inside the function itself, right, we cannot change the array that, that PTR points at. And the return value is also by value instead of by reference. So the return value itself cannot be used, for example, in an assignment statement to change the array that PTR is pointing at, which is the intention with this. So what we're also seeing here is that even though the parameter list is exactly the same for both versions of operator bracket, the fact that this one is const is enough to distinguish it from the other version of operator bracket. Because you might also recall going back to chapter 11, right, that when you have a constant, or chapter 9, that when you have a constant object, it can only call constant functions. So we know that a constant object cannot call a non-constant member function. So that's enough to distinguish these two versions of the subscript operator or operator bracket. So whenever we're working with a constant array object and we use the bracket operator, it's going to call this version of operator bracket. And if we're working with a non-constant object, then it's going to call the non-constant version of operator bracket. So in this case, right, there is no dummy parameter because this is different than the issue of prefix versus postfix. Right, because of course with prefix and postfix, you still have to, in either case, right, you're changing the current object, or if it's a friend function, then you're changing the first of the two objects that you pass in, or the object that you pass in. But here, since it's not going to change anyways, with this other version of operator bracket, we can just distinguish it that way. So const, in this case at least, is enough to distinguish it. So no dummy parameter is needed here. And we'll look at those first, and then we'll, because when we look at so this is the shallow copy version of the array class, which is going to have some issues, and then we'll look at the deep copy version as well. And the differences between the two really come down to the copy constructor and the overloaded assignment operator. So things like the bracket operator is going to be the same in both the shallow version and the correct version, which is what we call the deep copy version of this array class. But we'll start with those bracket operators to give you an idea of what that logic is going to look like. And so here, this is the non-constant version of operator bracket, right? The one that also returns the reference return type. And so we have a little bit of exception handling here. So we have some checking things like if the index number that was passed in is outside of the range. We have a throw statement there for, and that's an exception that's called out of range. So we've seen invalid argument come up a lot, but that's just another type of exception in this case, because if this is statement here is true, then that means that the number that we passed into operator bracket was outside the bounds. But otherwise, we just do this return statement here. So this is where we actually access, right, an element in the array of integers. So you'll notice there it just says return PTR, the name of the member variable PTR, and then the number that we pass in here is used as the index number. And then because we also know from our previous discussions on pointers that, you know, the brackets, the bracket notation and the star notation is really the same, right? In the sense that we can use either notation with the name of the array or with a pointer that points to the array, in the sense that if we say PTR bracket 1, right, that's also the same as star parentheses PTR plus 1. Here we're showing it in terms of the bracket operator, right, because that, you know, is also the name of this function. But that's what we're doing here. So we're using this integer number that we pass in to choose which location in the array that PTR is pointing at, which of those locations to access. And then we return a reference to that particular integer from the array, which can then be used in the application program to actually change, you know, that value in the array or that location in the array, which is why we have the reference return type here as well. And for the other version of operator bracket, it's really the same idea in terms of the body or the logic, except the return value cannot be used to change the array either. So this one here, we have the same, the validating the range. So the index number has to be between 0 and size -1. And if it's not, then we throw the out of range exception. Otherwise, we return, in this case, a copy of that element from the array. But the return statement is the same also in both of the two versions of operator bracket. So it's just that this one returns a copy, the other one returns a reference. And then since this one's also const, right, that also means that inside the function itself, right, we can't change anything. But the functions themselves, right, neither of them is actually trying to change anything, because the whole idea is that what you're going to be returning with the non-constant version is the reference to the location in the array, and then you'll be changing it in the application program. Which in the context of operator overloading, we don't really consider that dangerous like we did back in chapter 9, because that's the actual normal intended usage of the non-constant version of operator bracket, right? So we want to be able to do things like we said in the comments, array 1, where that's the name of the array class object, bracket 0 equals 5, right? We want to actually be able to change the array of integers in exactly that kind of way. So in that sense, we don't really consider this dangerous in the same way that we did with the time class example from chapter 9, because that was a little bit of a different situation there. So that's considered okay. And again, you'll notice that we make some exceptions to some of these rules for operator overloading. Like, for example, whenever we overload something as a non-member function, right, we've been making it a friend, so that way that function can access the members directly, right? Of course, we don't normally just go and make everything a friend, right? We're normally very mindful and careful about what we make a friend versus not make a friend. But the idea in the context of operator overloading is it's just more convenient to have those functions have direct access, as opposed to having those functions have to always go through, a set function or something like that. So we make, some exceptions to some of these rules for operator overloading. So what would normally be considered a dangerous reference return is really considered perfectly fine in terms of the non-constant version of the operator bracket, because that, again, that's how we want to be able to actually use it in the application program. So those are the two versions of operator bracket. Again, aside from the fact that one is constant, one is not constant, and the differences in the return type, the actual logic, right, in the body is the same for the most part, except for the different wording we use in the cout statements. But so the key focus here, though, really is also on the copy constructor and the overloaded assignment operator. Because the way in which we implemented the both versions of operator bracket is fine, right? In a minimum, right, you need the return statement, but we did a little bit more with the input validation and all that. But where the problem really is going to come into play with this version, with this shallow copy version of the array class, has to do with the copy constructor and the overloaded assignment operator. And let's take a look at those and see what's going on there. So here we have the first one is the default, right, constructor. This one just takes an integer. This one itself is fine. This constructor is fine. So what this default or what this one argument constructor does is it initializes size with the value that we passed in. And there's a little bit of exception handling here too, with the question colon and the throw statement. So if the size is greater than 0, then we're going to go ahead and assign that to the size member variable. Otherwise, we're going to throw an invalid argument exception. So just a little bit more exception handling on the constructor side. And then notice that, and this is in the member initializer list, right? So all of this here is in the member initializer list for this first constructor. But then notice what the second thing says, PTR, and then parentheses new int size. So that's where the dynamic memory allocation starts here. Because going back to our discussion on pointers, right, you've talked about pointers at 165, and we talked a little bit about them here a couple weeks back as well. You might recall that operator new, what it returns is a memory address, but it's a memory address from the heap area of memory, which is where things that we allocate dynamically are stored. So what this is doing here, right, inside the parentheses, the part that says new int size, well, the idea at that point is if we make it to here, at that point, we've copied the value from the array size parameter to the member variable size. So at this point, the member variable in the object size, it stores what array size has. And so what this is doing is it's dynamically allocating a new array of integers on the heap, and the size of that is determined by the size member variable. So if size is 5, then we're going to allocate space on the heap to store 5 array integers back to back. And what operator new also does is it returns the starting address of that array, which is why a pointer, right, is always needed to do dynamic memory allocation, because new returns an address and we have to store that address somewhere. And right, the only type of variable that can store an address would be a pointer. So that's what we're doing here with the second part of the member initializer list, is we're saying in effect, right, PTR equals new int size, dynamically allocate a new array of integers on the heap, and then store the starting address of that array of integers in the member variable PTR. So now, once we form that connection between PTR and the dynamically allocated array of integers on the heap, Well, now we can do anything we want with that array through PTR, since PTR points at the beginning of that array. And what it does from there, and we have with some of these functions, we have cout statements so we can see when we're inside of that particular constructor or function. But what we have here in terms of the loop body is a for loop that is going to initialize the array, meaning the actual elements in the array itself, right? The array of integers on the heap. And so what it's doing in this case is we're just storing 0 for each spot in the array. So the loop here goes and it loops over size, right? Meaning the member variable size. And on each loop iteration, notice that we say PTR, which is just a pointer of type int star, right? So PTR bracket I and then equals 0. So when that's done, each element in the array is going to be storing 0. So that's what the default constructor does. And that one is okay so far, but we are going to have problems with the copy constructor and the overloaded assignment operator. But that gives you an idea of what the default constructor needs to do. It needs to initialize size. And again, we're doing a little extra here with the exception handling to check for an array size that is not at least 1. So if we have like a 0 or a negative number, we're going to reject that and throw an exception. Otherwise, we're going to copy the value of array size into the size member variable and then dynamically allocate the new array of integers and have PTR store the address of that. And then in the loop body, we build that array by initializing each index to 0. Okay. So that's what it means. So PTR is just going to be storing the starting address of the array. And then from there, since that's the case, we can use either notation as far as accessing specific elements, right? Just like we talked about when we reviewed pointers. So here we're using bracket notation, but we also have a comment here that that's the same as the usual equivalent star notation, right? So PTR bracket I is just the same as star PTR plus I with the PTR plus I in parentheses. So that's what the default constructor is doing, just initializing each element in the in the array to 0. So that's fine, but let's keep going through this. And here's where we start to have some major problems. So here we have the copy constructor, which is going to take in an array object by constant reference. And so the shallow version of this is just going to copy the member variables from one to the other, right? Which we did that in the chord class, but that was fine, right? Because the chord class does not have pointers to dynamically allocated memory, just has the integers x and y. Here, it's going to be a major problem. So what we're doing in the shallow copy version of this is we're basically saying, right, current object size equals array2copy dot size, current object PTR equals array2copy dot PTR. So that's what we're doing. That's the default behavior of things like the copy constructor, right, and the assignment operator. So what we're doing here is also what the default version would be doing if we didn't write this out ourselves, right? Except it wouldn't be doing the cout statement, but it would be doing those two statements that we have here. But we need to think about why that's a problem, because it certainly is going to be a pretty significant problem, because it's not really doing what we need it to do. Now, the way that we're copying size is fine, right? That's just saying that the size of both, so the size of the two arrays for the two array objects is going to be the same. The problem really is this part here. PTR equals array2copy dot PTR. Well, okay, but what that's doing is that's copying the address in array2copy, that object's PTR, into the current object's PTR field. So now what you've done is you have two different objects, both of which their PTR member variables are both pointing at the same one dynamically allocated array of integers on the heap. So there's really only one array, right? And both array objects are pointing at that one array of integers on the heap. And that's not a true copy, right? If it were a true copy, then there would have to be two separate array of integers with each object pointing at one of them, right? So that way one object could, change its array, meaning the values in its array of integers, without affecting the other object's array that it's pointing at. But we're not doing that, right? Because we're just simply copying the address of, as it says here, right? We're just copying the address of one pointer to the other. And that's what we refer to as a shallow copy. So a statement like this is what's making it a shallow rather than a deep copy or a true copy. So that's a problem, and we'll see some of the implications of that in the application program when we run it for this shallow copy version. And then let's look at the overloaded assignment operator, which has basically the same problem come up once again. And the assignment operator here is very similar to what we did in the chord class. So we have the constant reference return type and the parameters passed by constant reference. But then notice the two statements here. Size equals write.size, PTR equals write.PTR. So same exact issue as the copy constructor, right? Because once again, we're taking the address in the write object, where write, for example, would refer to the array object from the application program, right? But we're taking that object's PTR field, whatever address is stored there, and now we're copying it over to the current object's PTR field. So we once again have the situation where there's only really one array of integers on the heap, and both of the two different array objects are pointing at the beginning of that same array. So we don't have a true copy. So it's the same problem as we encountered in the copy constructor. So we're doing a shallow copy in the copy constructor, And we're doing a shallow copy also in the assignment operator or operator equal function. And then we have some other operators here as well, but those are the two that are a problem, right? Everything else is fine, including the two versions of the bracket operator. It's really the copy constructor and the assignment operator that are going to have to ultimately be done in a different way if we want to be able to make a true, what we call deep copy, where you actually have copied the entire array to another location on the heap, which is what we would want to actually do. But the rest of this are just some of the other operators that we've seen. So for example, we have the equality operator, which what this is doing is it's just going through the array, right, for both objects, and just comparing the elements at the at the same indexes to determine if the two arrays are the same. So the idea here for equal is we first start by comparing the sizes of the two arrays, meaning of the current array object and the other array object, which is the one that we're calling right here. If the sizes are not the same, then you can go ahead and return false, because you know that the two arrays, meaning the array of integers on the heap, right, are not going to be exactly the same. And if that's not the case, then we should return false for equal. If they are the same size, then we loop over that size and compare the elements one by one, right, at corresponding indexes. So compare the value at ptr index I against right.ptr.I. So compare current object, ptr I, that location on the heap for that array against the other objects array on the heap. And if at any point you find that the values of the corresponding index are not the same, then just go ahead and return false, because the two arrays are not equal. And so the only way that we return true is if we make it through this entire loop without returning false, right? Then we know at the end that we can return true because the arrays are in fact equal. So that's op equal. We looked at the bracket operators, and then we have the input and output operators. But since we have to deal with the array, right, everything here is done in terms of a loop. So for the input operator, you'll notice that we just loop over the size, meaning the size of the array object that we're passing in. And then we get input for each of those locations, right? So that can be used with a CN type statement where the user can build the array with user inputs. And then also we have an output function as well, which can be used to output the contents of the array. And again, that just loops over size and then builds an output string using that. So again, a lot of similarities to the chord class, but some differences, because now, since we're dealing with an array, we have to have loops, right, in some of these overloaded operator functions to deal with each index in the array. Okay, and then the other thing here is the destructor. This is also an example of where we really do have to have a destructor, because we have to think about cleaning up, right, the dynamic data. The whole idea was that we use new in the default constructor when we said ptr equals new in size, right? And so we have to also likewise release that memory when it's no longer needed. And that's going to take place in the destructor, right? Because we know from earlier in chapter 9, we said that the destructor doesn't release the memory itself, but what it does do is it gets ready to get to that point. Because one of the things that we said in chapter 9 was that the destructor does cleanup work, and we sometimes, you see that term, termination housekeeping, but that just really means cleanup work that you need to do to get ready to destroy the object. That's going to take place in the destructor, and then when the destructor finishes running is when we actually physically remove the object right from memory. In this case, we have to think about removing everything, right? The object itself and the array that it points at. And so the idea is that since the array of integers that the PTR member variable points at was allocated dynamically with new, to remove that and clean that up from the heap, we have to use delete, right? Because if you think about the destructor here, the object itself, right? So if you imagine the application program, if we just say something like, array ARR1 with a number passed in, like array ARR1 5, because we saw with the default constructor that you can pass in a size. When that object itself goes out of scope, right, it'll be destroyed, because that was one of the things that we learned going back to chapter 9 when we talked about, objects at different scope levels and when they're destroyed. So a regular, non-dynamic local object is going to be destroyed, right, when it goes out of scope. Then we also talked about things like static and globals, right? But here, it's not just the object that we have to think about, right? You have to also think about the thing that PTR is pointing at, which is a dynamically allocated array of integers. How are you going to ensure that that is also cleaned up and removed from memory when you're done using it? Well, the idea is that, if we just do nothing and, don't put in our own destructor and just use the default version, then we're not going to be cleaning up that array of integers, right? We're not going to be removing it from the heap when we're done using it, because the default destructor does not have a delete statement in it. So it was important here to write out our own destructor, because we do need to make sure to release that memory from the heap as soon as we no longer need it, which is when the object is about to go to scope, right? Because certainly it follows that if we're about to destroy the array object, which has PTR as member variable and PTR points to that array, if we're about to destroy that object, then we certainly don't need the array of integers on the heap anymore that the object was previously pointing at. So what we can do there is we just need to have this delete statement in the destructor. So the idea being that when the array object itself goes out of scope, we're going to enter the destructor, and before destroying the actual object, before that happens, right, we're going to remove the array of integers from the heap. So that way, by the time the destructor is finished running, we've removed both things, right? The array object itself has been destroyed, but the array of integers that PTR was pointing at has also been destroyed. So that way it's not just hanging or dangling in memory. So in that sense, we're cleaning up everything related to the object when the object itself actually gets destroyed. And now, certainly it also would be possible to apply this concept of dynamic memory allocation to the array object itself, right? Meaning, for example, in the application program. And that's fine as well. Here we're talking about, though, dynamic memory allocation in terms of the array of integers, right? Which is separate from talking about making the array object itself dynamically allocated. That's something that you could do as well, right? Meaning, for example, use operator new in the application program and create the array object that way. And that also means that in the application program, when the array object goes out of scope, that you would have a delete statement for that, right? So the general idea is that every new statement should always have a corresponding delete statement. And so in the context of this array class, the array itself is always handled dynamically. The array object may or may not be created dynamically, right? That depends on what we do in the application program, right? Because you could certainly create an array object that's not dynamic, or you could create one also dynamically with the keyword new, which just means that in the application program, you would need to have a corresponding delete statement to, delete that dynamically allocated array object. So we just want to keep in mind also that in general, we can do dynamic allocation on both sides of this, meaning the array object itself could be, if we wanted to, created dynamically as well. That's why we have that in the destructor. So we just saw in this case that new was used in the constructor, delete was used in the destructor. And so every new should have a corresponding delete. So that's what the destructor is doing for us. And now the application program, since we've looked at the class code here. So let's look at this first block. And we'll start to see what's going to happen here. So what we've did is, and this is within main, right, in our application program, but what we did was we started by creating a couple of array objects. And so that constructor takes in an integer value, that first constructor, where that number that we pass in is the size. And then we do a couple of other things here inside of this first block. So for example, we have statements like int1 equals int2. And then we have some comments here, but that's going to invoke the overloaded assignment operator. And then we have the statement array int3 curly bracket int1, which we know that that's going to invoke the copy constructor because that's creating a brand new object from int1. So let's go ahead and then there's other things here too, which we'll eventually look at some of these. But let's see first what's going to happen with that, with the first block here, meaning the block that goes from here to here. So we had an exception that was ultimately thrown, right? So we've had something, happen that shouldn't have happened, and we'll see what's going on there. But let's think about things like the invoking of the copy constructor and the overloaded assignment operator. And are those perhaps causing issues for us? Well, they are actually in a couple of different ways, really. But there's a particular reason, right, why this is crashing and throwing the exception. So a couple of things here. So first we're saying int1 equals int2. That invokes the assignment operator. And the PTR field, right, the address in int2, its PTR is copied over to int1. So the end result of that is now int1 and int2 are both pointing at the same array of integers on the heap, which itself already is not good, but that's what's happening, right, as a result of this statement. Furthermore, now we create yet another array object, int3, and we make it a copy of int1, meaning what? Meaning that we copy the size field from int1 to int3, and we copy the PTR field from int1 to int3. So now we end up with three different objects all pointing at the same, right, the same array, the same dynamically allocated array of integers. Because see, in the beginning, we created int1 and int2 through the default constructor. So we, in the beginning, had, two different arrays. But then we did this statement here, which changed int1, both its size and PTR fields, to be the same as int2. And then we also created this third object, int3, and made it a copy of int1, which at that point is also a copy of int2. So now we have three different array objects, all pointing at, right, the same array of integers on the heap. That already in and of itself is not good, because it means that, right, if we change, for example, if we go in and we try to change something with int1, and then we do a cout of that same location in the array with int2, you're going to see the change, right? Because they're all pointing at the same array, which we really don't want that, because we really want each array object to have its own array that it points to, and no other array object should point to that same array, because that's what we mean by a true copy, right? I can change one without affecting the others. So maybe, at some point I do want to make int1 a copy of int2, but I should still be able to later go into int1's array and change any of the numbers and not have that affect int2. So that's a problem. Another issue that comes up here, though, is in terms of the what's happening on the destructor side, in terms of the crash. Because remember, so each of these objects are going to go out of scope, right, when you hit that right curly bracket. But think about what's happening in the destructor. Well, the destructor has the delete statement, right? Delete bracket PTR, meaning wherever PTR is pointing at, delete that. And we use the brackets there because we have to use that version of delete for removing an entire array of dynamically allocated data. But so each of the three objects is pointing at the same array of integers on the heap. And so when we destroy the first object, we go to its destructor, we encounter the delete statement, that's going to remove the array of integers from the heap. But then when we just try to destroy the second object, we try to do the same thing again. But at that point, right, the array has already been removed from the heap. So we get a crash here because we're trying to delete something that's already been deleted. So that's yet another problem that comes up with a shallow copy, is we have these unintended consequences where things that would normally not crash the program are now crashing the program, right? If this was done properly, then this whole block here, right, would not crash the program. Meaning if we did a true deep copy, then this block here would not crash the program. But since all three of the array objects are pointing at the same array of integers on the heap, because there's only really one array of integers on the heap, you destroy the first one, and that much is okay, right? Destroying the first object. But then when you go to destroy the second object, now you hit that delete statement and that object's destructor, but the array's already gone, and we're crashing because we're attempting to delete something that's already been deleted. It's already been removed. So that's the problem that we're running into here. And in particular, we know the order of destruction here because we talked about that back in chapter 9, the rule of reverse order. So what happens then is we destroy object int3, and that's going to go through because that's the first one that we destroy. But then next we try to destroy int2, and that's the problem, right? Because it's pointing at the same location on the heap, which at that point has already been removed. So that's what's causing the crash. So that's why we're saying that there's really major, really significant issues, right, with this shallow copy version. Because stuff like this should not be crashing the program. And it wouldn't be crashing the program if we handled the copy constructor and the assignment operator in the correct way, which is what we'll see at next week, right? So next week we'll continue this, and we'll look also at the deep copy version, which is the correct way of handling this. So the difference is with the deep copy version, what would happen is you would end up with 3 different arrays on the heap, and int1 would point at one array. int2, its PTR field would point at a second array on the heap. And then int3, its PTR field would point to the third array on the heap. And then you don't run into all these problems that we're running into here. So stuff like this wouldn't crash the program. And we would also be able to change any of the arrays without affecting the other. So in other words, we have what we call a true copy or a deep copy. Whereas here we use the phrase shallow copy because it's not really a true copy in the traditional sense that we think about it, since there's only really one array to begin with. And so that gives you an idea of some of the issues here. So we'll continue that going into next week. And then after we finish up operator overloading, then the next major topic we'll look at will be inheritance in chapter 11. Okay, so we'll go ahead and end it there for today.